Okay, so we arrive at the final objective of 1.7, infinite limits. We talked about it in an informal way. Now we're going to talk about it in a formal way. So here come those epsilons and deltas. Infinite limits can also be defined in a precise way. Let f be a function defined on some open interval that contains the number a. Okay, so we always picture, here's a, there's an open interval about a, so everywhere here except maybe at a itself possibly, and function is defined there. Then the limit as x goes to a of f of x equals infinity means that for every positive number m, there's a positive number delta, such that if positive absolute x minus a is less than delta, then f of x is greater than m. So now there just needs to be an m here, number m, so that the function, well, if it's in this interval, it'll be up here eventually as x gets close to a. This says that the values of f of x can be made arbitrarily large, as large as anyone wants, larger than any given number m, by taking x close enough to a, sufficiently close to a, within a distance delta where delta depends on m. Okay, so we're going to do the same kind of seeking a delta that we did before, but with x not equal to a. So here's a geometric illustration. Okay, kind of the same thing I was doing on the previous slide. Okay, x is getting close to a, this thing's blowing up, and the function y equals f of x is just getting arbitrarily large as anyone wants. Pick the biggest number you can think of, we can make it larger, just by making x get closer to a than it was before. Given any horizontal line y equals m, we can find a number delta such that if we restrict x to lie in the interval a minus delta, a plus delta, right? Delta we usually think of as a tiny, tiny number. So there's this little tiny interval about a, and if we can get in there with x, then if that means that the function blows up and is way up here, has a value greater than m for any m that anyone wants to pick, then we will have proven an infinite limit. The curve y equals f of x lies above the line y equals m. You can see that if a larger m is chosen, if we want to be, if we want m to be up here, then we're going to need delta to be smaller. So here's a problem. Here's an example. Use definition 6, the same one we've been using, to prove that the limit as x approaches 0 of 1 over x squared equals infinity. Okay, so I always want to keep the graph in mind. So here's our function, something like that. Oops, not like that. And x is going to approach 0, and the function is going to get large. Let m, okay, so now here's where we start using the definition. Let m be a given positive number, whatever you want it to be. we want to find a number delta such that if positive absolute x is less than delta, then 1 over x squared, the function that we're given, is greater than m. We can always get greater than m for a little delta. Okay, so now here we are, with this function 1 over x squared, and we're, thinking, we're going to try to reimagine that in terms of, reimagine the inequality in terms of absolute x. Of course, a is 0, right? A is 0. F of x is 1 over x squared, and L is infinity, if you can say that, in this oxymoronic topic of infinite limits. Okay, and so we need a delta such that if positive absolute x is less than delta, then, well, then this thing is true. But that means flip both sides, right? Take a reciprocal of both sides. And when you do that, you might have forgotten this, but the sense of the inequality changes. Okay? So flip both sides, the sense of the inequality changes from a greater than to a less than. And so now square root of both sides, and we do have absolute x. We do have absolute x. And if you have a square root of 1 over m, that's a square root of 1 over square root of m, which is 1 over square root of m. Didn't have to say it that way, but we can say it that way. Now, I don't want this square root symbol to be here. So let's see if I can get rid of it without messing up the audio. Okay, so now we have a suggestion for delta. We're going to choose delta equals 1 over square root of m. And so we're going to show that whenever we've got this, the if clause, positive absolute x less than delta, then we're going to be able to say the other thing. Okay? So now let's take this and this, okay, and so absolute x less than, right? Absolute x less than 1 over square root of m. Okay. Now, we flip both sides. 1 over absolute x greater than square root of m over 1. Square both sides. That's just m on the right. That's just m on the right. And 1 over the square of 1 over absolute x. Okay, well, if you're squaring, you don't have to say absolute. 1 over x squared. Okay, so 1 over x squared now is greater than m, and that is what we had to show, right? Anytime we've got positive absolute x less than delta, then, if then, come on pen, if then, this is true. 1 over absolute x less than delta. This proves the limit. This shows that 1 over x squared goes to infinity as x goes to 0. We have proven this limit according to the definition, that the limit, right, this and this as just shows that we are able to make a similar this limit definition for the definition. The limit as x approaches 0, the negative variety, 1 over x squared, we're able to say that the limit as x approaches a number is negative infinity, and we just make a little adjustment in the definition. Now we, instead of saying f of x greater than a number m, now f of x is always going to be less than a number n, and that's how we have to define an infinite limit of the negative kind. Okay, so maybe y equals the negative of 1 over x squared. Whoops. So here's that graph. Okay, and there's a number n that we could always go below as x goes to, for example, 0. I'll get it done for 1.7. See ya in 1.8.